For centuries, the world of science operated on a deeply comforting assumption. The universe is just a predictable clockwork machine. The logic was simple. If you understand the physical laws governing that machine, gravity, mass, momentum, you can wind the gears forward to see what happens next. It's how astronomers know exactly when a solar eclipse will cast a shadow over a specific city hundreds of years in the future. But if you zoom in on human-scale systems, that mathematical certainty falls apart. We can plot the exact trajectory of Jupiter, yet we cannot reliably predict a sudden stock market crash or a shift in global economics. Historically, scientists assumed this was just a hardware problem. We thought human society and earthly environments were just too complicated to calculate by hand. The belief was that once we built powerful enough computers to gather all the data, we would finally predict everything. In 1961, an MIT meteorologist named Edward Lorenz tried to do exactly that. He built a weather prediction model using one of the world's first computers, feeding it a dozen variables like temperature, air pressure, and wind speed. During one run, Lorenz wanted to save a little processing time. Instead of entering the exact starting variable of 0.506127, he typed in the rounded number from his printed output, 0.506. When he returned to check the machine, the new forecast simulated an entirely different weather system. That tiny omission, a difference of less than 1 part in 1,000, proved that absolute prediction in a complex system is a mathematical impossibility. The formal term for what Lorenz discovered is sensitive dependence on initial conditions. You probably know it as the butterfly effect. The popular myth suggests a butterfly flapping its wings in Brazil generates the energy to cause a tornado in Texas. In reality, not a single flap of a wing simply alters the initial atmospheric air currents by a tiny fraction of a millimeter. That microscopic shift puts the entire atmospheric system on a new trajectory, eventually rewriting the outcome weeks later. This diagram illustrates the core math of nonlinear systems. If you make a microscopic change at the starting line, the difference does not scale at a constant rate. The gap between the two outcomes amplifies exponentially as time moves forward. These tiny initial errors snowball, completely overwriting the system's expected future state. You can see this clearly with a pendulum. A single weight swinging on a pivot is a highly linear system. If you know its starting angle and mass, you can easily calculate its exact path until friction brings it to a stop. But if you attach a second pendulum to the bottom of the first, you create a double pendulum, turning a simple, predictable machine into a highly sensitive, chaotic one. Look at this simulation of two identical double pendulums dropped simultaneously. Their starting positions differ by a fraction of a millimeter. At first, they swing in perfect unison, but as that microscopic difference amplifies, they violently split into completely different, unrepeatable trajectories. Here is the paradox. Neither pendulum is behaving randomly. They are both following the exact same laws of gravity and momentum as a grandfather clock. Chaos is what happens when physical rules play out with such extreme sensitivity that our ability to measure them breaks down. If microscopic changes make the future unplottable, you might wonder if we are just floating in a completely random, patternless void where anything can happen at any time. We aren't. Mathematicians describe chaotic systems using a concept called boundedness. This visualization is a Lorenz attractor. The lines represent the changing state of a chaotic system. They never cross and they never repeat the exact same path twice. The specific future is unpredictable, but the outcomes are trapped inside a distinct geometric shape. Translate this to weather forecasting. A meteorologist cannot tell you the exact temperature 30 days from now, but the boundaries guarantee it will never snow in the Sahara Desert. Even if we blanketed the Earth with perfect weather sensors every single square meter, the microscopic spaces of air between those sensors would still contain unmeasured variables. Over a few weeks, those invisible gaps would exponentially amplify and ruin any long-term model. This same sensitivity dictates the behavior of human-made systems, global supply chains, our financial markets, and sprawling urban infrastructure. We often treat these networks as predictable machines, optimizing them for maximum efficiency by removing every bit of slack from the system. But in a nonlinear environment, That lack of redundancy makes us brittle. A minor delay in one shipping port or a slight algorithmic error on a trading floor has no room to dissipate. Instead, it amplifies through the entire interconnected web. Because reality refuses to follow a clockwork script, we have to rethink our engineering. Instead of stripping out redundancy for a perfect, fragile efficiency, we must design for chaos-absorbing resilience.